Okay, so in this lecture, we're going to talk about absolute convergence, ratio, and root test. Now, these two tests will prove useful in determining radius of convergence for different powered series that we meet in this course. Okay, so we'll start with a definition. The series sum an is called absolutely convergent if the series some absolute value an converges. This is the definition of absolutely convergent. Okay, so you look at the series, and then you look at the corresponding series where you take the absolute values of all the ANs instead. So, remark, if the terms AN are positive, then absolute convergence is the same thing as convergence. And that's because ANs, if they're positive, they're equal to their own absolute value. Okay, we'll have a look at some examples. Are the following series absolutely convergent? Okay, so you're going to look at the series, then you're going to look at the corresponding series where you take the absolute values of the terms, and you're going to see, does this new series converge? So are the following series absolutely convergent? First example, sum of -1 to the n over 2 to the n, from n equals 0 to infinity. Second example, sum from n equals 1 to infinity, -1 to the n plus 1 over n. Okay, so at this point in the video, I think it'd be best if you just pause it and try to see for yourself if you can figure out, are the following series absolutely convergent, A and B? Okay, so hopefully you took some time to attempt the questions. I'm going to run through the solutions now. A, we had the sum, and we want to look at the absolute value now because we're asked is it absolutely convergent of the absolute value of -1 to the n over 2 to the n from 0 to infinity. So if we take the absolute value of -1, we get just 1. So this is a half to the n from 0 to infinity. And this is equal to 1 over 1 minus a half. Now, how do I know this? This is by the formula for a geometric series, which we've seen before. So by formula for geometric series, which I'll remind you is sum r to the n equals 0 to infinity, equals 1 over 1 minus r. And this is only valid for absolute value of r less than 1. And in our case, r is a half, so this formula is valid. So we have 1 over a half, which is equal to 2. Now you might have seen a different version of the formula for a geometric series where you had an a, but this formula is just a version where a is 1. Okay? So hence, sum n equals 0 to infinity -1 to the n over 2 to the n is absolutely convergent. Okay, second example. We had sum. Now we want to look at absolute value -1 to the n plus 1 over n. And n went from 1 to infinity. So as with the last case, when you take the absolute value of -1 to any power, you just get 1. So this is going to be sum 1 over n. This should look familiar. It is the harmonic series. And we know from the previous lecture that this diverges. Hence, sum minus 1 to the n plus 1 over n equals 1 to infinity is not absolutely convergent. Okay, so we've seen an example of a series which is absolutely convergent and an example of a series which is not absolutely convergent. Again, absolute convergence is if you take the sum, instead of the ANs, you take the sum of the absolute values of the ANs and you check, does this new series converge? Okay, so we'll continue with a definition. A series, sum AN, is called conditionally convergent if the series itself converges, so if it is a convergent series, but the corresponding series of absolute values diverges. So this is the definition of conditionally convergent. So you are convergent, but not absolutely convergent. That is conditionally convergent. Example. So this example has a name, the alternating harmonic series. And we've seen this very recently. It was this series from the first example. This was the example B, minus 1 to the n plus 1 over n. So we've seen this does not converge absolutely, because if you look at the absolute values, you actually get the harmonic series, which you know diverges. So this does not converge absolutely. Now I claim that this does in fact converge. So if you do not take absolute values, if you just look at the series given, this series does converge. Now, for proof of this, I want you to look at the notes. So see notes for proof of convergence. Okay. So this is a series which converges but is not absolutely convergent. So this is conditionally convergent. NB, this is an important example. Remark. So why are we talking about all this stuff? Why are we talking about absolute convergence? Well, remember, we're trying to deal with power series. So for a power series, sum Cn, so power series centered at A, equals 0 to infinity, with radius of convergence R. First point, the series converges absolutely. So not only converges, the series converges absolutely for absolute value x minus a less than r. Second point, the series diverges for absolute value x minus a greater than r. And undetermined for absolute value of x equal to r. So for different power series, you may or may not have convergence on the boundary when x minus a, the absolute value of that, equals r. So you must check these points individually. Okay? So this remark says that inside this open interval around A of radius r, you have absolute convergence. Because remember, for a power series, for different x, you get a different series. So what this remark says is that if x is less than r away from A, when you plug that x into your power series, you have absolute convergence. If you have an x that is further than r away from A, if you plug that in, you will diverge. And then if x is on the boundary, if it is exactly r away from a, you don't know. So you have to check these x's individually by plugging them into your power series. Okay, so we'll move on to our first theorem. If a series is absolutely convergent, then it is convergent. Okay, so what this theorem says is that absolute convergence is stronger than convergence. If you converge absolutely, you also converge. Okay, and this actually, if we think about it, there's some intuition behind this. What are we doing when we're looking at a series? We're taking these ANs and we're adding up more and more of them, and we're looking at the limit as we add up more and more ANs. Now, taking the absolute value of the ANs forces them all to be positive, the same sign. So when you're adding up all these little lengths, they're working together in their attempt to diverge. So if you still converge when they're all working together, so if you have absolute convergence, then you're going to get convergence when they're potentially working against each other, i.e. having positive and negative. Okay? So absolute convergence is stronger than convergence. Remark: the converse is not true. So convergence does not imply absolute convergence. Example, well, we've already seen an example. N equals 1 to infinity of minus 1 to the n plus 1 over n, the alternating harmonic series. This is a series which converges but does not converge absolutely. So i.e. convergence does not imply absolute convergence. And this is reassuring, otherwise our definition of conditionally convergent was pointless. So conditionally convergent was convergent but not absolutely convergent. Example. So we want to see how can we apply this theorem. So are the following series convergent? First example, sum n equals 1 to infinity minus 1 to the n plus 1 over 3 to the n. Second example, sum n equals 1 to infinity sine n over 4 to the n. Okay, so on the surface, these two series are quite complicated looking. You have an alternating series, and then you have this sine n in the second series that's going to have quite complicated behavior. So hint, test for absolute convergence. So see if you can make the absolute values of these ANs either less than something simple or equal to something simple. And if you can prove that these two series converge absolutely, then you're going to get that they converge. So at this point, pause the video, try and see if you can prove that these two series converge or not by testing for absolute convergence. Okay, so hopefully it's some time to attempt the questions. We're going to look at the solutions now. First problem, sum n equals 1 to infinity of, now we're going to look at the absolute value like the hint suggests, minus 1 to the n plus 1 over 3 to the n. Again, if we take the absolute value of minus 1, we just get 1. So this is sum n equals 1 to infinity of 1 over 3 to the n. Now this is 1/3 over 1 minus 1/3. And this is the formula for a geometric series with first term a third and multiplier 1/3. And this is equal to 1/3 over 2/3. Is equal to 1/2. So our original series is absolutely convergent. So hence, sum n equals 1 to infinity minus 1 to the n plus 1 over 3 to the n is absolutely convergent. And hence, by the theorem, it must converge. Okay, because absolute convergence implies convergence. Second example, this one was a little more complicated. Sum n equals 1 to infinity, absolute value sine n over 4 to the n. Okay, so we have to work a bit harder with this one. Now, what is any series? Any series is a limit of partial sums. What's the definition of a partial sum? Sn is where you add up the first to n. So n equals 1 to n of sine n over 4 to the n. And we're going to look at the absolute values. So Sn is a sequence. And it's a monotone increasing sequence. What does that mean? So to go from Sn to Sn plus 1, I add on the absolute value of something. So I add on a positive number. So these Sn's are getting larger, because at every stage I add on something positive. So it's a monotone increasing sequence. Hence, if I show that Sn is bounded above, it must converge by the monotone convergence theorem. So if you have a sequence that's getting larger and larger and it's bounded above, we have by the monotone convergence theorem, it must converge. And if this sequence of partial sums converges, that's exactly what it means for the series to converge, because the series is the limit of the partial sums. Okay, so I'm going to have to turn to a new page. Okay, so let's try to establish this bound. So sine n is stuck between minus 1 and 1 for all n greater than or equal to 1. We know this. So this implies the absolute value of sine n is always less than or equal to 1 for all n greater than or equal to 1. Hence, sine n over 4 to the n, if I look at the absolute value of this is less than or equal to 1 over 4 to the n for all n greater than or equal to 1. Now, the term on the right-hand side is a much simpler looking term. So hence, Sn, we can bound this by if we were just to sum the 1 over 4 to the n's. And we only take the first n of them. That is less than or equal to if we're to take the limit, because all of the 1 over 4 to the n's are positive. But this is just a geometric series. So this is equal to 1 over 1 minus a quarter, which is equal to 4 over 3. Geometric series. Hence, Sn is bounded above by 4 over 3, and by the monotone convergence theorem, it must converge. So hence we've shown that the sequence of partial sums converge. That's exactly what it means for this series to converge. So i.e. equals 1 to infinity, Sn is absolutely convergent. So we showed that the sequence of partial sums where we're taking the absolute value converges. So this series is absolutely convergent. And by the theorem, this sum, sine n over 4 to the n, is convergent. Okay, so this theorem came in very handy because we had quite a complicated series. The sine n has strange behavior. It hops around as n gets larger. Yeah, it'll hop it from minus 1 to 1 and values in between that. So its behavior is quite strange. But we're able to, using the absolute value, compare that to the behavior of a much simpler series, a geometric series. So the theorem came in useful because it allowed us to compare this complicated series to a simpler one and show that it converges. Okay, so now we're moving on to one of the main items in the lecture. This is the ratio test. So let some an be a series, so any series, positive or negative terms, and we define L to be the limit as n goes to infinity of the absolute value of an plus 1 over an. So L is the limit of absolute value of the ratio of successive terms. So an plus 1 over an. So if L is less than 1, then the series converges absolutely. And hence by the theorem, and hence converges. 2, if L is greater than 1, then the series diverges. Third point, if L equals 1, then the test is inconclusive. So if L equals 1, the ratio test tells you nothing. You don't know if you have divergence or convergence. So, what's the intuition behind this? Intuition. So if L is this limit of an plus 1 over an in absolute value, this would tell us that the absolute value of an plus 1 is roughly equal to L times the absolute value of an, as n gets very large. So this starts to look like, if you want to go from an plus 1 to an, you multiply by L. So it starts to look like a geometric series with multiplier L. That is the absolute values of the terms. So if you were to take the sum of the absolute values of the ANs, as n gets very large, it starts to look like a geometric series with multiplier L. So then if you go through the points, this almost looks like the requirement we had. If the absolute value of R was less than 1, we had convergence. If it was greater than 1, we had divergence. Okay, so that's the motivation for the ratio test. Okay, so let's look at some examples. First example, sum n equals 1 to infinity of minus 1 to the n minus 1, 2 to the n over n factorial. Second example, sum n equals 1 to infinity n to the n over n factorial. Third example, sum n equals 1 to infinity minus 1 to the n times n over 5 to the n. Fourth example, sum n equals 1 to infinity minus 1 to the n over n squared. So, use the ratio test to test the above series for convergence or divergence. And say, so if the test is inconclusive, say so. Okay, so if we look at these examples, we can see there are quite complicated algebraic objects in it. So take the first example. We have an n factorial. What is n factorial? N factorial is n times n minus 1 times n minus 2, and you keep multiplying down the numbers until you get to 1. Okay, so the behavior of this series is going to be pretty complicated. So the ratio test is going to prove invaluable when trying to determine whether these type of series converge or diverge. So let's start working through the solutions. First problem. So what was an in the first problem? An was minus 1 to the n minus 1, 2 to the n over n factorial. Now I want to use the ratio test, so that involves an plus 1. So what would that look like? Well, we just replace every n we see in the expression for an with an n plus 1. So we get 2 to the n plus 1 over n plus 1 factorial. Hence, remember we want to look at this limit L, so lim n goes to infinity, absolute value of an plus 1 over an. Now if I want to look at dividing by an, I can look at multiplying by it flipped. So lim n goes to infinity, absolute value of an plus 1 times 1 over an. So when I'm filling in, I'm just going to invert the expression I have for an. So lim n goes to infinity, absolute value, filling in for an plus 1, we just have minus 1 to the n because the plus 1 and the minus 1 cancel, 2 to the n plus 1 over n plus 1 factorial, times flip an. On the bottom now we're going to have minus 1 to the n minus 1 times 2 to the n under n factorial. Now, we want to see what cancellations we can do. Well, the 2 to the n will cancel with the 2 to the n plus 1, just leave us with a 2. The minus ones we don't care about because we're taking absolute value. Now, how do we deal with the factorials? So what was n factorial? N factorial was n times n minus 1 all the way down to 1. N plus 1 factorial is going to be n plus 1 times n minus 1, and again all the way down. So the only difference between the top and the bottom, we get all these cancellations, is that on the bottom we have this extra term of n plus 1. So this is equal to 1 over n plus 1. Now I'm going to fill that into the limit. Absolute value 2 over n plus 1. And this is 0. In particular, it's less than 1. Hence, by the ratio test, we got this limit L was less than 1. So, by the ratio test, this series converges absolutely. And in particular, it converges. So it converges, not only actually converges, it converges absolutely. So this shows us how powerful the ratio test is. We didn't have to look at the limit of partial sums, which is what the actual series is. We just looked at the limit of the absolute value of an plus 1 over an. We established that was less than 1, and from the ratio test we just get absolute convergence. Okay, let's look at the second example. In the second example, an was n to the n over n factorial. So again, I need an expression for an plus 1. And again, everywhere I see an n, I just replace it with n plus 1. So, I want to look at this L, which is the limit of an plus 1 over an is equal to n plus 1 to the n plus 1 over n plus 1, and again I'm dividing by an, so I just flip it and multiply by it. So n factorial is now on top and n to the n is on the bottom. Now, I want to see what sort of algebraic cancellations I can get. So I'm going to write n plus 1 to the n plus 1 as just n plus 1 to the n times n plus 1. And I'm dividing that by n plus 1 factorial times n factorial over n to the n. Now, why am I doing that? It's because I want to combine this n plus 1 to the n and this n to the n. So, this is n plus 1 to the n over n to the n times, what have I left over? I have an n plus 1 factorial on the bottom and an n factorial on the top. And they have an n plus 1 left over. So, what cancellations do I get? Well, this is the limit of 1 plus 1 over n. If I divide the n into the n plus 1, I get that. the n factorial over n plus 1 factorial will leave me with 1 plus 1 over n plus 1 times n plus 1. So this is equal to, the n plus 1 cancels with the n plus 1, I'm just left with this. So you might recognize this. This is E, which is roughly 2.71. In particular, it's greater than 1. So we found that this L for this series is greater than 1. So hence, this series diverges by the ratio test. So move on to the next page. A remark, if you're confused about the last point of how that limit was E. So remark, in particular, the limit as n goes to infinity of 1 plus x over n to the power of n is equal to e to the x. And this is for all x. Now, how could you show this? Well, you can show this using logarithms, continuity, and L'Hopital's rule. Okay, so hopefully you've seen this before. If not, this is how you can attempt to prove it. Exercise. First exercise of the lecture. Do problems. So do examples 3 and 4. Okay, and if you're confused about this e to the x thing, please email your instructor. I'm sure they'll be more than happy to explain it to you. So now I'll move on to the second test mentioned in the lecture title. This is the root test. The root test. Okay, so as with the ratio test, let sum an be any series. The difference here is now we're going to let L be defined to be the limit as n goes to infinity of the absolute value of an inside an nth root. So what's the conclusion? If, first case, L is less than 1, then the series sum an converges absolutely. And in particular, converges. So remember, absolute convergence implies convergence. Second case, if L is greater than 1, then the series diverges. Third case, if L equals 1, then the test is inconclusive. So if L equals 1, the root test tells you nothing, just like in the case of the ratio test. So what's the intuition behind this? So if we look at this limit L, so L is equal to limit n goes to infinity of the nth root of the absolute value of an. So this would tell us that for large n, the absolute value of an is roughly L to the n. So absolute value an is roughly L to the n for large n. So hence, the sum of the absolute values behaves like a geometric series with multiplier L. for large n. So this sum of absolute values of an, its tail, so the terms for large n, the sum after a certain n, starts to behave like a geometric series. So if we look at the cases, we get this L less than 1 corresponds to this absolute value of R less than 1, etc. Okay? So the intuition for this is very similar to the intuition for the ratio test. Okay? The idea is that the tail end of the series starts to behave like a geometric series, and this L is the multiplier. It plays the role of the multiplier. Okay, so let's look at some examples. First example, sum n equals 1 to infinity minus 1 to the n minus 1 times 2n over n plus 1 to the power of n. Second example, sum n equals 1 to infinity 2n plus 1 under n to the power of n. Third example, sum n equals 1 to infinity ln n over n to the power of n. So, in particular, the root test, is useful for series with powers of n in the terms. Okay, so if you're to try and establish convergence or divergence by looking at the partial sums, you're not going to be able to get a nice formula for the nth partial sum. So you need to establish these tests. The idea here is that if you have a power of n, making the terms in your series complicated, then the root test is a very good candidate for trying to establish convergence or divergence. So at this point, pause the video and attempt these examples. Try to see if you can figure them out for yourself. Okay, so let's work through some solutions. First example, what was an? An was, in the first case, minus 1 to the n minus 1 times 2n over n plus 1 all to the power of n. So we want to look at the absolute value of this term. So the minus 1 to the n minus 1 will die, and you'll just be left with 2n over n plus 1 to the n. So hence, the nth root of the absolute value of an, which is what we want to ultimately take the limit of, is just 2n over n plus 1. This gives us that L is equal to lim n goes to infinity, nth root, absolute value an, is equal to lim n goes to infinity of 2n over n plus 1, which we know to take the limit of this, we divide top and bottom by n, because it's the highest power on the bottom. So we get 2 over 1 plus 1 over n, that's just equal to 2. In particular, this is greater than 1. So hence, this series sum minus 1 to the n minus 1, 2n over n plus 1 to the power of n diverges by the root test. Okay, so second solution. In the second example, an was n over 2n plus 1, all to the power of n. And this tells us that its absolute value is, well, it's positive, so it's just itself. So we want to take the nth root of this, That's just going to kill that power of n. So we're left with 2n plus 1 under n. So hence, L is equal to this limit of n over 2n plus 1. And we know how to take this limit. We divide top and bottom by n again. So we're left with 1 over 2 plus 1 over n, which equals a half. In particular, half is less than 1. So, hence, the series sum n equals 1 to infinity, n over 2 to the n plus 1 to the n converges. It converges absolutely, and it converges. But in this case, that's the same thing because all the terms are positive. This is by the root test. Okay, so exercise. Do example 3. Hint, because this is a little more complicated. So instead of taking the limit over n, extend to a limit over real numbers, so over x element of r, and use L'Hopital. Because to use L'Hopital, you take derivatives, so we have to be talking about a limit over the real numbers. Okay, so we're going to end the lecture with a challenge. Not an exercise, but a challenge. And I'm going to put it in between stars, because challenges are fun. So, given that the alternating harmonic series, which we have seen from earlier, and what was this? This was the sum from 0 to infinity, minus 1, to the n over n plus 1, converges. Use the above fact from the previous lecture, so this ln of 1 plus x, the fact in the white box above, which you have from the last lecture. Use this and continuity of ln to show that this alternating harmonic series, so sum from 0 to infinity, minus 1 to the n over n plus 1, actually equals ln2. Okay, so that's the challenge. Good luck.